Hey everyone, welcome back to another video here on the channel. In today's video, I got the perfect video here for you because what we're going to be doing is we're going to put the low versus high kV conversation to rest once and for all. We're going to take a look at each brushless motor and we're going to see which one comes out on top. Now in the previous video, what we did is we had two different kV values and we ended up seeing which one came on top when we ran them at the exact same voltage. And as you probably would have guessed, it was actually unfair for our low kV brushless motor. So what we're doing here in this video is we're going to take a look at two different kV values. I have two brushless motors here of the exact same series, and each one of these has a different kV. One of them has a kV of 1840. We're going to take that particular motor and run it on 8S, and the other brushless motor has a kV that is roughly double than that, and it's at 3650 kV, and we're going to run that guy on 4S. Now one of these motors has exactly double the windings, double the turns, so to speak. So we would expect that both these brushless motors, when you double the voltage, should be a great comparison, and that's ultimately what we're after here in this video. We're going to calculate some gearing and throw these motors into the car very shortly here, but before we do, I want you to leave in the comment section below which brushless motor do you think is going to come out on top? Is it going to be the low kV motor or the high kV motor, or does it even matter at all? Now, as you're doing that, another thing I'd highly suggest is make sure that you're subscribed to the channel. I did hear that if you are not subscribed to the channel, the likelihood of letting the smoke out of your ESC is quite high. I don't want you to do that. Make sure you're subscribed. Now let's jump right into it and take a look at some gearing. We're on the RCexplained calc sheet here in order to find some gearing for our V2 limitless build, high versus low kV. If you're a member of either tier 1 or tier 2, you will gain access to download a copy of this for yourself. We do a lot of battery testing here on the channel, and we ultimately reveal the true C ratings of these packs. And let me tell you, they are a lot different than the labeled C ratings. And as you can imagine, battery manufacturers are not really willing to send me battery packs to only show that the numbers they post are completely inaccurate. Only one battery manufacturer has the confidence in the power and performance of the pack that they build and has sent it to me. All others we pay from the patrons who support the channel. You guys have my back and I appreciate it. Thanks a lot. Let's now take a look at the gearing speed chart, and we're going to go through the first set, which is going to be our low cell count and high kV. We know that we're using a 4S pack for our 3650 kV brushless motors. I'm going to put a note here for 3650, and we also are going to have another one that's going to be 1480. Those are two brushless motors that we are using here today. So the first thing that I need to do is adjust my gearing. Now we're not using the V1 limitless here today. That is taken. So I switch over to the V2 and it updates all of the gearing here on our chart. Now the next thing I want to do is change the gearing. Now I know that 158 miles per hour is not going to be achievable. So what I do is I go and change it to the maximum size I can fit in physically into that V2 limitless. I think it's around 46 tooth. That's at least the largest that I have right now. I'm going to place that in there. Now we're at 134 miles per hour, still very far away. So we need to get that down. We're going to go to 30. That's still too much. We're going to go to 28. We're still too high, 26, not looking good. We're gonna go to 25. So at 25, we're still seeing 105 miles per hour. It's getting in there into the zone that we are looking for. The next thing that I wanna do is update our load factor and figure out the loaded current at speed and the average IR per cell. And what we're gonna do here is look at the loaded current. Now we know from past runs that we expect on 4S to be somewhere in the neighborhood of around a couple hundred amps. So I'm going to leave it actually at a perfectly even 200. Next thing that we're going to do here is we're going to update our average IR per cell. Right now it's showing as 4. We want to update that to 1 milliohm because that is the pack that we're running. On average, we're expecting 1 milliohm there. And the next thing that we're going to do is we're going to adjust our max voltage per cell. We're probably not going to be 4.2 by the time we start our run. So it's a good idea to drop this down by a little bit. So let's say, 4.17. Now we're being really critical here, but we're trying to do the best we can with the values that we can enter. So our max voltage per cell is now a little bit lower, representing that we burn a little bit of power from where we're standing all the way to the starting line. Now the last thing we got to deal with is this 8% load factor. Now this is the kicker. We ended up thinking in the last video that if we go and update our value to over 20%, it would be ideal. We left it at 15%, but then in actuality, we know that it was well beyond that 20%. So in this video, I'm going to go with a 25% mark. It probably is even more than this, but we're going to leave it at 25% and cross our fingers here. Magically, that gets us to the 100 mile per hour mark. I don't know if these motors have enough in them to actually achieve that. That's quite a big ask from a motor of this size. So you're going to see this motor appear here a lot in this video. Next thing we're going to do is quickly change this over. 8 cell and our kV, it's not actually 1480. I keep doing this. It is 1840. I switch up the numbers and don't realize it until later. So 1840 is the value that we're going to put in here. Now the difference here is we're still going to be 25% loaded, but this is not going to be the case with 101 miles per hour. We're using a different battery set. We're only going to be around 100 amps or so, and I have to factor in a few things here to our average IR. The connectors that we're using are a little bit different. I'm expecting this to be around 3 milliohms for this particular set. So the batteries did perform better than this, but I'm factoring in a little extra for the connectors in anticipation of seeing a good result here. So 161 versus 158. I think we have a good comparison in the values that we have. We do get an extra little bump with the 1840 because if I look at the comparison of this versus that, it's not quite 2.0. There's a 1% difference. This kV here, if the 3650 was the same, it should be 1825 that our other motor is. So this is the difference, 1825 versus 1840. So not a perfect combination. It's kind of funny though, because this motor is exactly 2 times the turn count of the 3650. I think this is a 2Y and this is a 4Y wind. So we're gonna go with this gearing and see where we end up. We're gonna do like what we did in the previous video. Let's watch it here together. All right guys, here we are, high voltage setup. I'm just gonna grab the phone here, make sure we track and start. And then we got some motion there on the speedo. Good, so we can see it. All right. So I'm sending out the car right now, and as we go through this process where I send the car in and retrieve it, we're gonna speed up this process. So right here, we get the car turned around and we're gonna go for our first rip. Gotta love it, so cool. Again, we're fast forwarding.
We'll bring it back in and we're going to check the temperatures here.
Yeah, because that's one of the concerns that I have is temperatures, because we couldn't get gearing slower. So here we go, we're starting that process. Turn on the gun and point it towards the motor. It's that simple.
So highest that I saw was 73. Mostly 70. It's probably cooling down at this point. So somewhere around 70 is the general temperature of this motor. Now we get to check that speed, see what we hit. So we can stop now and read 154. That's quick. It's really quick.
That is really quick. You know, hit that like button for these tiny motors going that fast. That is some serious
we're tracking.
speed.
After that, we switched up the ESC and we're gonna send it.
So this is now not the ESC that I changed out. You know, this is me focusing on too many things, saying the wrong word. We are definitely swapping out the motor there, and now we got the 1840 kV in there.
We are clear, and we're off.
Fast. What do you think? We bring it back in, and I'm gonna get this
thing our way back here. We got down there. We should see some pretty good speed. I'm gonna get the temperature right away once it's back.
Again, I'm still worried about that temperature, and I know that I held it a little bit more than the last run.
90 degrees. I saw 90, we got 82, 93, 91, 90, 93.
That's hot. That's really hot. A lot hotter than I'd like to be.
So more. This is all the same gearing. Roughly the top speed is the same. And now we can check the speed. We're going to stop and read 147. Wow, I'm actually quite surprised. We're going to have to take a look at the data and see exactly how that happened. Let's go take a look at the data and talk about it.
Let's go. Here is our graphs, and you guys will want to stick around because I'm going to take both of these motors and I'm going to place them in a dyno, and we're going to get actual performance. We're going to measure RPM, we're going to measure torque, and compare these things at 100% throttle in a much more controlled environment to see how these things compare. Let's take a look at our data set and then we'll get closer to that point. So for S, we are seeing that we pull the trigger here, and over the course of several seconds, almost 4 seconds total, we end up getting to this point. So within 4 seconds, this is where I finally was confident that the car is tracking true, and I gave it full trigger. We ate up a bunch of distance doing that, so that's a penalty that we pay in order to get this thing rolling properly. Once I was comfortable, this is where I gave it full trigger, and you can see that we get to 100% throttle output. You always want to make certain you're at 100% throttle output. This is how we know we're getting the maximum out of the motor and the speed control combination. And then we hit our maximum current rate at this maximum throttle output, and then it begins to ramp down. And what we're going to do is we're going to check just the very end here, and at the very end we're somewhere around 14.5 volts, and imagine that we're at that 198 amp mark. Now I'm going to take a couple data sets from this graph and we're going to use that to compare against the ADAS once we see the next test method that I'm going to use. Let's jump into the ADAS graph here and take a look at what that looks like. Here is our ADAS graph. This is all panned out for you. So we see that the acceleration of this was much cleaner. We ended up accelerating, and then this is the point where you can see the power output actually is pulled a little bit and then given back in. So what's happening in this case is that we were not confident until this point. We actually gave it a little bit more throttle in the last pass, actually quite a bit more throttle, and then we gave it full trigger after about 2 seconds when we were confident the car was tracking truly in straight in order for us to make a pass. Then it took another couple seconds to hit that 100% throttle, and then we can see that maximum current again reached when we hit 100% throttle right there. We're going to see that every time we make a speed run pass. And then near the end, you can see a couple things happening. If we take a look at the current here, it's like 96, 97. And if we look at the very end of this graph, we also have somewhere around that 96, 97. What this is telling us is that we actually had a couple seconds more that we ended up running this car than we needed. This is going to contribute to excessive amounts of heat because we didn't need to pull the trigger for this much time. Our maximum speed more than likely was reached somewhere around where my mouse cursor is, meaning 2 seconds earlier than compared to where we held full trigger. So we're going to take a couple measurements here as well, 27 point something, 28 volts, whatever the numbers are. I'm going to take a point from this. I'm going to take a point from the last graph, and then we're going to compare that after I have a bunch more numbers. Let's jump into now a dyno run. Now this is a very exciting point in the video where I've put a lot of time, effort, and even some frustration came out of that too. But we're essentially after the most consistent results where we get to control the environment and come out with a scenario with the best results that you'll probably ever find on the internet when it comes to a comparison of low versus high kV, both in a practical test and a lab test where we get dyno results. So essentially what you're seeing here is the dyno result. We're really after the torque value. We get that by using the dyno where we set up our brushless motor, we apply a load. This is the 3650 kV motor that you're now starting to see spool up. I'm going to continue to talk about the setup. It measures torque by using these 2 load cells. It also measures thrust for fun. We don't care about that in this test with this load cell here. So all that works in combination. And then what we need to get RPM, voltage, and current, because if we did it with that load cell, the dyno load cell, we would blow the electronics up because we're over 100 amps on that 2S setup. This is the XLX2 that we're using for RPM, voltage, and current. So that's our 3650 kV brushless motor. Now I just switched it over into the 1840 kV brushless motor, and essentially what I've had to do here is test it multiple times. I had to charge up a battery, and I couldn't use the SMC because it just put way too much power out. I had to use one of my weakest batteries because I had a weak 3 2S's all in parallel just to get the 2S values. And then we used a 4S, and what I'm after here is matching the torque values that we just saw. So I got that information. Now I'm going to go and compare those two values, combine all the metrics, and I'm going to show you the chart where we keep that torque value consistent. Here's the charts that represent all the data that we've collected here in this video, and this was done over 2 or 3 days. So we have on the left-hand side our speed run results. Let's go from top to bottom and run right through this. This is obviously a comparison of high kV versus low kV, 3650 versus 1840. I have some brushless motor specs in there, and then we get into the more significant factors. The first one being is the 100% power time. In our high kV brushless motor is 4.5 seconds, where a low kV motor is 6.4. So those 2 seconds is more than likely what brought the temperatures from 72 degrees Celsius all the way up to the 90 degrees Celsius mark. And then when we look at the voltage at speed, this is the second factor that played into the overall speed that we got. The 150 something versus the 140 something for our low kV brushless motor. Because we had a lower voltage on the lower kV, this is the result of that lower overall speed. Now, this is a great note for all of us, is that on our high kV brushless motor, I used a really good top of the line battery pack and had a direct connection right into the ESC with no other batteries in the line. I also used the best connector. I love the AS150 connector. It's my favorite for radio controlled airplanes, boats, and cars. It's a great combination connector. There's obviously better out there, but this is a really good one. The problem here with the low kV brushless motor is I don't have 2 4S packs right now. That would be an equivalent that I can use in this vehicle with those AS150 connectors. I had to use some EC5s and get them converted to go into the ESC, and this causes significant amounts of voltage drop, and even under lower loads. I didn't think it would drop this much. The packs are still really good, and it still did. Those ES5 connectors, guys, I don't like them. Try to get them out of your system. If you're using anything more than 80 amps in your power system, this is stealing and robbing power from you. There is a voltage loss across those connectors, and this is where you can see it. It was significant. You can see the number below. I'm only running half of that current. 198.8 amps is what that high kV brushless motor was operating on, and then our 96.6 volts caused more of a voltage loss with still really good batteries, but because of those connectors, we only saw 3.5 volts, and overall our speed dropped by quite a bit. The wattage that we saw, 2880 versus 2700, the RPM that I recorded from the data log there that you saw was 42,800 versus 40,800. So those 2,000 RPM represent the difference there in the overall speed that we achieved. Now I ran through some numbers here just to see what's going on in the high versus low kV. That's where I use the RM. I just do some very simplified copper losses and iron losses to see what's going on in these two brushless motors. Our copper losses on the high kV was 209. Our copper losses in the low kV was 198. Iron losses in the high kV brushless motor 39, and iron losses in the low kV brushless motor is 28 watts. Now the overall losses in watts is 249 versus 226, but keep in mind that we pulled more power for the high kV, so we would expect there to be more losses in that motor that used more power. The difference in efficiency, this is the loss percentage of the motor using simplified copper and iron losses, works out to 8.6 and 8.35. Essentially, what this is telling us as a conclusion to this small little tidbit is that the difference in efficiency between one motor and the other motor is almost identical, less than 0.5%. We're talking even between 1.25% of a difference there is essentially negligible between both of these motors. These motors should perform nearly identically, but did not, because I couldn't keep all the factors the same when I did that test. And this wasn't the only test I made. I made multiple passes, and I took what came out to be the best to show exactly what happens. We'll come back to this in the conclusion that we make after we talk about the dyno results. So the dyno results here is really cool. We start off by taking that torque. I'm going to jump to the torque value because what I did is I wanted to take a value that matched in torque. That's why I made so many passes to figure this out with the dyno, and then I had to load the motor and bring the battery voltage down by several passes you saw there. So if you go back to those data sets, you will be able to pick a line where I take all those values from, including even the speed run that we did as well. So the torque value that I took was 0.326 Newton meters on the high kV brushless motor, and the torque value on the low I took is 0.325, so 0.001 difference. And what's really cool then is we jump up to the motor RPM when I go and take those results now from the ESC at the exact same point in time. I get 21,179 RPM on the low kV and 21,222, so a little bit more RPM, and we see that with a little bit more torque. These differences are almost negligible and essentially are the same RPM and the same torque value. Then we see the power that we get now in watts. This is mechanical power. You could also equate this to horsepower by dividing this by, I think, 746. So we're almost 1 horsepower on this setup. And if you look at that, we are at 724 watts of power, mechanical power on our high kV setup, and our low kV is 720 watts of mechanical power there. That is essentially the same. Now let's take a look at our electrical power that goes into it. We have 6.8 volts on our high kV, 143.6 amps. This is why it would blow up my dyno electrical circuits. And then the power in watts, 976 watts. Remember, this was a continuous value. We were pulling 143.6 amps continuously in that run until I then pulled the throttle back. So 976 watts versus 13.9 volts, 70.3 amps continuous, and our power is 977 watts. This is the electrical watts. Now we can do an exact efficiency between mechanical and electrical wattage. We get an efficiency of our high kV brushless motor at 74.2% and our low kV at 73.8%. This kind of data, guys, is absolutely cool. I love to see this, and this is coming out to exactly what we should expect with these brushless motors. All right, guys, I want to give you my conclusion based off of the results that we achieved here in this video with both the speed run as well as the dyno test. When it comes to low versus high kV brushless motors, both of these setups can produce nearly identical results where you will not see a difference between one versus the other. What's more going to impact your setup is the things that I encountered, where if you're using more voltage, if you're using more connections and you don't do that efficiently, you are going to see a drop in performance within that specific region. This is what I saw as well. Same idea happens within our ESC. If you don't get an ESC that is capable of a higher amount of current and doesn't perform as efficiently with higher current like our XLX2 did in this particular video, you are going to see an overall reduction in overall efficiency within that setup. So ideally, your setup is more important than whether you choose a high or a low kV brushless motor. So who takes it, the low or the high kV brushless motor? Well, really, it's an equal match. Both of them perform equally as good, and it more depends on your setup than anything else. Optimizing your setup to produce the most amount of power is the best way to go, whether you choose a low kV option or a high kV option. Just know that both of them work very well. Now you can take this video and send it out to the many other people out there that are comparing the low versus high and don't know which one of these wins the true battle. Thanks a lot for watching. See you in the next one.